Good morning, everyone. So, uh, we continue with the last day of our conference. So, it's an immense pleasure to introduce Sam Payne from U Texas, who is going to tell us about top weight homologies of MG. Sam?
Thanks, Ludwig. Yeah, so it's great to be here, and I'm sorry to have missed some of the talks earlier in the week. I'm sort of simultaneously here and at the intro workshop at the ICERM semester on combinatorial algebraic geometry. And so the topic I gather is sort of Hodge theory and moduli, and often it seems the focus is really on sort of period maps and using Hodge theory to extend and compactify moduli spaces, and I'm just going to take a slightly different take on that, and so I'm going to study a moduli space, and then I'm going to study the Hodge theory on the cohomology of the moduli space. So I realize this is a sort of a variation on the spirit of what's being talked about, but I hope it will be there will be something of interest for many of you. And so the goal here, as I say, is to study Deligne's mixed Hodge structure. So on now the cohomology of MG. So so from now on, so unless I say otherwise, all cohomology will be with Q coefficients, and I'll just leave the coefficients out. And so part of this mixed Hodge structure is that we have the increasing weight filtration, which is supported in degrees from 0 to twice the dimension. And so when I say top weight, I'm meaning the top graded piece of this filtration. So this would be the 6G minus 6 graded piece of the weight filtration on the cohomology of MG. Or if you apply duality, so this is, you could take weight 0 compactly supported cohomology of MG and take the dual. And so since we've mostly been talking about sort of variation of Hodge structure and period maps, and we haven't been talking about cohomology of moduli spaces and the Hodge structures on those. So let me refresh your memory. So some background information on the cohomology of MG. So in particular, so first thing to remember is that the cohomology of MG is completely understood in low degrees. So this is a famous theorem of Madsen and Weiss, and so this is now from almost 15 years ago. This was conjectured by Mumford decades before that. And so in small degrees, so this is degrees less than something like 2/3 G minus 1, then the cohomology of MG is a polynomial ring generated by the kappa classes, which are, so kappa I is in degree 2I. And things to note here is that this is, so all of this is pure weight, and all of this is in even degree. And so here so the theorem is due to Madsen and Weiss, and the conjecture is due to Mumford, but this is sort of the culmination of work of many people. So John Harrer in the 1980s showed that the cohomology of MG does stabilize, so that there is some stable cohomology ring. So as G increases, and then it was Ulrike Tillman who showed that that the cohomology of MG stabilizes to the cohomology of an infinite loop space. And so that brings to bear the techniques of stable homotopy theory on this problem. And then Madsen and Tillman made a specific conjecture on which infinite loop space it is, whose cohomology is the stable cohomology of Mg. And then that conjecture of Madsen and Tillman is what Madsen and Weiss proved. And once you have that specific infinite loop space, then it's not hard to compute the cohomology and show that it is this ring that Mumford had conjectured. And so there's now several proofs of Mumford's conjecture, the Madsen-Weiss theorem, and all of them use homotopy theory, stable homotopy theory in some way. And so for those of us who are algebraic geometers, this conjecture came from algebraic geometry, and I think it's still very much an open problem to have an algebrogeometric understanding of this. And so in the context of a Hodge theory conference, so one thing I should emphasize is that this these proofs, so since they're coming from stable homotopy theory, they are treating Mg as a topological space. They're treating it as the classifying space for the mapping class group. And treating it as a topological space explicitly ignores the Hodge theory. So the mixed Hodge structure does not play any role here. And of course, you could have different algebraic structures on the same complex manifold that give rise to different Hodge structures. And all of that is ignored by the topological viewpoint. So in the course of this talk, part of what I want to get at is sort of what the algebraic point of view, what the Hodge theoretic point of view can bring to bear on the problem of understanding the cohomology of Mg in the unstable range, so outside of this small range of degrees where the cohomology is completely understood by topological methods. Okay, so let me continue reminding you of what has been known for decades about the cohomology of Mg. And so one of the things that's known is that the cohomology is much, much larger than the stable cohomology. And so this is a theorem of Harrer and Zagier from '86. So again, by sort of combinatorial and topological methods, that the Euler characteristic of Mg, so it eventually alternates sign. It becomes negative when G is even and positive when G is odd, and it grows like G to the 2G. So it's growing super exponentially, and meanwhile, so if you go back to the stable cohomology, so it has generators in one generator in each even degree, and so then you can estimate the dimensions of this stable ring using the partition function, or the Hardy-Ramanujan estimates for the partition function. And then what you'll come up with is that the dimension of, so this is what's called the tautological ring. So this is the subring generated by the kappa classes. And this is less than some constant to the square root of G. So in particular, the full cohomology of Mg is much, much larger than not just the stable cohomology, but the subring of cohomology generated by stable cohomology. And moreover, there's enormous amounts of odd cohomology on Mg, at least when G is even. And one of the things that Harrer and Zagier point to in the original paper where they do this computation is that at the time of their writing in 1986, there was not a single known pair GK where K is odd, such that HK of Mg was known to be non-zero. So there were no known examples at that time of non-vanishing odd cohomology groups. And there was very little known about the unstable cohomology, so cohomology that is not expressible as a polynomial in kappa classes. So since that time, there has been some progress. So examples of unstable cohomology. So here the most famous example is a computation of Lohenga from 1993, and he showed that H6M3 has rank 1, so it's isomorphic to Q, and the weight there is 12. So this is the first known example of a top weight class, and it's there for G equals 3. And then a little over a decade later, in the PhD thesis of Ursula Tomasi, we got the first example. So almost 20 years after Harzaghi, we got the first example of a non-vanishing odd cohomology group, which is also unstable, and that's H5M4, which has rank 1 and weight 6. And I think sort of as of 2018, this was the only known non-vanishing odd cohomology group on MG. So we know that there's lots of odd cohomology out there, and I think it's a tantalizing problem, a tantalizing challenge to understand where it is and what structure it has. And so part of what I want to communicate to you is that Hodge theory, and in particular the mixed Hodge structure on the cohomology of MG that comes from its algebraic structure, so thinking of it really algebraically and not just topologically, allows us to find non-vanishing odd cohomology groups. So this is work with Melody Chan and Chan and Galatius that builds also on old computations in a very different context, and I'll explain how the two contexts are connected as the talk goes along. But so these are computations of Bar-Natan and Mackay, and computations of Vilvacher and Zivkovich. And so putting these computations together with some observations on the Hodge theory, the cohomology of MG, we get that H15 of M6 is not 0, so that's the middle cohomology group on M6. Also, H23 M8 is not 0. H27 of M10 is not 0. Okay, so we can give lots of examples in higher genus and high cohomological degree. So degrees in genera that were previously outside of the realm of what was accessible, we can now sort of find these non-vanishing groups. And the reason why these groups are not 0 is because the top weight part is not 0. So we can identify one graded piece of the weight filtration, which is accessible to computation and which is not 0. Okay, so we've talked about the low degree cohomology. We've talked about what little has been known about odd cohomology and top weight cohomology, and now some examples of the new progress that one can make. And so let me say a little more about the progress that one can make. And so another place where one might sort of hope to be able to make progress is, so if low degree is understood, then let's try to understand the highest possible degree. And now let me remind you again, so background of what has been known for decades about high degree cohomology of MG. And so here, the fundamental fact is a theorem of Haar from 84, which is that the virtual cohomological dimension of MG is 4G minus 5. So that means that if you take any local system on MG, then its cohomology vanishes in degrees above 4G minus 5. And there exists a local system whose cohomology is non-vanishing in degree 4G minus 5. So in fact, part of what Haar proves is that the mapping class group is a virtual duality group and of virtual dimension 4G minus 5. And so there's the Steinberg module, which has cohomology of rank 1 in degree 4g minus 5, and that Steinberg module can be thought of as the reduced homology of Harvey's complex of curves. So that's an infinite rank local system on MG that has cohomology of rank 1 in degree 4g minus 5. What that doesn't tell us immediately is whether the singular cohomology, so cohomology with coefficients in the trivial local system, whether that is vanishing or non-vanishing in the highest degrees. And so this is a theorem that was known in unpublished work of Harrer, and it was published simultaneously, so 2 different proofs by 2 different methods, by Church-Farb-Putman in 2012, and Morita, Sakasai, and Suzuki. So I think the preprints appeared right around the same time, so essentially simultaneous. Publication was off by a year, but what both groups proved, and what was previously known to Harrer, is that H4G minus 5 mg vanishes. So the singular cohomology vanishes in top degree, and this is for all G. And so, okay. These proofs were by 2 very different methods. So Church-Farb-Putman are using group homology and explicit structure of group cycles for the mapping class group, and Morita, Sakasai, and Suzuki are using methods inspired by mathematical physics. So they're relating, so using work of Kontsevich that relates the cohomology of MG to Lie algebra cohomology of certain infinite dimensional Lie algebras. In both cases, you get an explicit combinatorial presentation for this group, H4G minus 5mg, and they're able to show that it is 0. Okay. And so there were some conjectures that came out of these ideas, so both ideas, so these group theoretic ideas and these Lie theoretic or mathematical physics ideas. And so let me tell you what the conjectures were, what the expectations were. So this conjecture, so this is a special case of a series of conjectures by Kontsevich from 1993 in his paper on formal non-commutative symplectic geometry. And this, the same conjecture was made, or the special case of the conjecture that I'm going to talk about was made independently by the same authors, Church-Farb-Putman, 20 years later. And the conjecture was that if you fix a positive integer k, then H4G minus 4 minus k mg is 0 for large G. And so this is saying that, so if you fix a distance below the virtual cohomological dimension, then eventually everything will vanish. So this is sort of a version of stability in the unstable range. And so to emphasize this, the relation to stabilization, so Church-Farb-Putman, they gave maps. So H4G minus 4 minus k mg to H4G minus k mg plus 1. So you fix the distance below the VCD and you get maps between the groups that increase the genus. And they showed that stabilization implies vanishing. So in other words, so if these maps stabilize, so if these arrows that they wrote down, and I'm not telling you exactly what the arrow is, but they gave it explicitly, and if this arrow is an isomorphism for all G sufficiently large, then both groups are 0. So that's a refinement of the conjecture. And so by studying this top weight part of the cohomology, Chan and Galatius and I have shown that these conjectures are not true. And so, and in fact, they're not true in the sort of very first case. So if you go from 4g minus 5 to 4g minus 6, and then so you can look at the dimension of h4g minus 6 mg, and this in fact grows exponentially with g, and this is for any beta less than, so beta naught, so the base of the exponential is like 1.32, and what this number is, so this is the real root of t cubed minus t minus 1. Okay, so we have a very explicit understanding of this exponential growth. And if you're interested in odd cohomology, we also know that the odd cohomology in top weight is growing, but we have a little less control over the genus and degree. So, okay, and so let me say that, so why can we show that this group is large? The reason why we can show it's large is because one graded piece, so the top weight part of it is large. So you could ask for top weight odd cohomology. So I mentioned earlier 3 top weight cohomology groups that were non-zero. And okay, so if you take the direct sum over all g prime smaller than a given genus G, and then if you look at the top weight part of the odd cohomology of those mg primes, then this also grows like beta to the g, at least. And so this is again dimension. Okay, so good. Okay, so h4g minus 6 is growing, and the odd cohomology is growing. And the reason why we can see that growth is again by appealing to Deline's mixed Hodge structure and identifying one graded piece of the weight filtration that we can understand more easily than the rest. So now in the rest of the talk, I want to tell you about how do we understand this top weight cohomology of mg. And so the way we're going to do it is by relating the top weight cohomology of mg to the singular homology of a tropical moduli space. And so I want to now explain to you how the topology of mg is related to the topology of the tropical moduli space. And one nice way of understanding this is through Teichmuller theory and semi-stable reduction. So I'm going to recall a few background details. So if we have X smooth and projective, genus G at least 2, and this is over some K, which is an algebraically closed non-Archimedean field. So algebraically closed rank 1 valuation. And so we have inside K, we have the valuation ring. So then stable reduction tells us that there exists a unique stable model. So this is curly X over spec R. And so the general fiber is our given smooth projective curve X, and the relative canonical sheaf omega X is ample. So again, over spec R. And because we're working with curves, this ampleness is just combinatorial. It's just that the degree on every component of the special fiber is positive. And so we want to understand what's going on combinatorially on the special fiber. And so we'll encode that. And so this is what people would call the abstract tropicalization of the curve X, or the skeleton of the curve X in Berkovich theory. And so what this is, so this is going to be a metric graph with some decorations. So this is the dual graph of the special fiber. So this is over the residue field. So little k is the residue field of the valuation ring. And so the vertices of this graph correspond to the irreducible components of the special fiber, and the edges correspond to the nodes. And so so I should say that the vertices are decorated by the genus. So vertices correspond to components, and each component has a genus. And the edges have lengths, and these correspond to the thickness of nodes. So if we have an edge E, so this corresponds to a node, so say PE, and this has some local defining equation. So the total space of our semi-stable model is locally isomorphic to something like xy minus f. So the vanishing locus of some xy minus f, where f is in the maximal ideal in the valuation ring. And so then the thickness, so the length of the edge is the thickness, which is the valuation of this element f. And just to sort of get something visually in our shared thinking, so just an example when g equals 2, so the stable reduction might be a genus 1 curve attached to a rational curve with a self node, and then the dual graph will have 2 vertices corresponding to the 2 components. The vertices are labeled by genus. When the genus is 0, I will omit the label, so we'll just label the vertices that correspond to components of positive genus, and a self node would correspond to a loop edge. So in these dual graphs, you could have loop edges, you could have multiple edges if 2 components meet at multiple nodes. And stability is just saying that every vertex of valence 0, of genus 0 or decorated by 0 has valence at least 3. And so valence is the number of half edges incident to the vertex. So here the loop edge contributes 2 to the valence. And so here's a vertex of valence 3. And so the tropical moduli space would be a moduli space of these decorated dual graphs that appear in this way. So this is the set of stable tropical curves of genus G up to isomorphism. And isomorphisms should respect all of the data. So respecting the edge lengths, respecting the genus markings on the vertices. And so this is a disjoint union over all combinatorial types, so over all possibilities for the underlying combinatorial dual graph, forgetting the edge lengths. And then there's some open moduli space or locally closed moduli space for that combinatorial type. And so for a given combinatorial type, all we can do is give a positive real edge length for each edge. So that's our positive orthant, but then we need to mod out by the automorphisms of the underlying finite graph. And again, those are automorphisms that respect the data, so respect the vertex labelings. And there's a natural topology on this, of course, where as edges contract as lengths go to 0. Okay, and so one sort of picture to keep in mind is that the shape of this tropical moduli space is it's cone shaped because you can just rescale the edge lengths by any positive scalar. And so this is the cone over, the cone over the link. And so we'll just normalize the link so that it becomes a subspace. And we'll just take the subspace of volume 1. So stable tropical curves, and this means one-dimensional volume. So the sum of the lengths of all of the edges should be equal to 1. So we have the cone over this compact moduli space. And rather than giving precise definitions, I'll do an example. So when G is 2, so here are the possibilities for the dual graph. So we could have a smooth curve of genus 2. We could have 2 curves of genus 1 that meet at a node. We could have a curve of genus 1 with a self node. We could have a curve of genus 1 that's connected to a rational curve with a self node, the example we looked at before. We could have a rational curve with 2 self nodes. We could have 2 rational curves with self nodes that meet at a node, or we could have 2 smooth rational curves that intersect each other at 3 points. And if you look at the relations that come from, so if you partially order by things that you can get from one to the next by collapsing edges. So for instance, with the barbell, we could collapse a loop edge and get to here, and we record the number of loops that have been collapsed to a vertex, or we could collapse the bridge and get to this bow tie graph here. So that's the sort of poset of strata, but there's more information in the topological space than just the poset because of the automorphisms of these graphs. So for instance, this graph has an automorphism that interchanges these 2 edges. And so the contribution of this type to the moduli space is not a cone, it's a cone mod Z mod 2. So let's draw the compact version of this. So we have vertices corresponding to graphs with 1 edge. And so we have 2 types with 1 edge. So we get 2 vertices. And so here's a vertex for this type, and here's a vertex for this type. And these graphs shaped like keys. So by putting a length t and a 1 minus t on the bridge and the loop, you can interpolate between the 2. So we get an edge between the 2. And the bow tie graph, so here there's an automorphism that interchanges the 2 loops. And so we don't glue on an edge, we glue on an edge mod Z mod 2. And if you collapse either loop, then you get to this graph. And so it's a half edge that is based at this vertex. And then similarly, so the barbells don't give us a triangle, they give us a triangle mod Z mod 2. And that's where it's glued on. And the theta graph, the full symmetric group S3 is acting on the edges. And so you glue on the fundamental domain, which is triangle mod S3, and it has 1 vertex, 1 half edge, and this is where it goes on. Okay, so there's a picture of the link of the tropical moduli space, so delta 2. And okay, so that's a contractible space. But as G increases, the topology of these spaces become more interesting. So let me say just a word about what we know about the topology of these spaces as G increases. So this is some recent work with Daniel Alcock and Dan Corey. And what we've shown is that so all of these spaces are simply connected. So if we go from delta 2 to delta 3, we actually get a space homotopy equivalent to the 5 sphere. When we go up to delta 4, the reduced rational homology of delta 4 is 0, but delta 4 is not contractible. There's a torsion in H6 and H7. So, okay, so these spaces eventually do have some interesting topology. And so now what I want to do is relate the topology of this tropical space to the topology of the complex moduli space. And so here, again, I want to recall that the complex moduli space is the quotient of Teichmuller space by mapping class group. So these are hyperbolic metrics on a closed orientable surface of genus G, and the mapping class group is the component group of orientation preserving diffeomorphisms of SG. So how are these related? So G is fixed, and so once G is fixed, then what we can do is fix some positive epsilon sufficiently small so that when we look at closed geodesics of length less than epsilon on a surface in this Teichmuller space, that these are simple disjoint and in distinct isotopy classes. So the fact that you can sort of do this, I think, is well known, and in particular, it follows from the work of Mirsakani on closed geodesics. And so once we've fixed this small epsilon, then we get a map that doesn't depend on any other choices. And if we vary epsilon, but keeping it sufficiently small, then the different maps that we get are homotopic to each other. So here's the map is from Teichmuller space to the tropical moduli space. And so X is going to map to GL, where G is the dual graph of the nodal surface obtained by collapsing all small geodesics. So geodesics of length less than epsilon. And so we have an edge that corresponds to a geodesic of some length, AE, which is strictly less than epsilon. And so then the length of the edge, which is not the length of the geodesic, but it is minus log of the length of the geodesic over epsilon. So that gives us a, okay, so there's something to check that the tropical curve you get in this way is stable, but it is. And so now we have a map. And in fact, you can check that this map is proper. And so then we have a pullback map on compactly supported cohomology with whatever coefficients you want. So you have the compactly supported cohomology of the tropical moduli space is now mapping into the compactly supported cohomology of the complex moduli space. This is just a nice ring map because it's coming from a map of spaces. And so topological methods don't give us much of a handle on this map lambda upper star, but Hodge theory does. So Hodge theory, going back to Deline's original arguments where he constructs the functorial mixed Hodge structure, that's giving collapses of certain spectral sequences. And so using Deline's theory, we can say, not with integer coefficients, but with rational coefficients, that the pullback is injective. And in fact, the image is weight zero compactly supported cohomology of the complex moduli space. And so you can use duality and long exact sequence of a cone and turn this around and say, okay, so then the top weight cohomology of mg is the Poincare dual of weight zero compactly supported cohomology. And so the H6G minus 6 minus star mg, so cohomology with closed supports, this is surjecting onto with a degree shift, the rational reduced homology of the link of the tropical moduli space. And the kernel is everything of weight strictly less than the top weight. So H6G minus 6 minus star MGC. And so that means that this reduced rational homology group of the link of the tropical moduli space, that this is canonically isomorphic to what we called at the beginning the top weight cohomology. So now this is a combinatorial topological object that we can try to understand and do computations with. And so this is what Chan, Galatius, and I have been doing and working on for some time. And so one of the ways that we try to understand what's going on this side is by identifying contractible subcomplexes of delta G. So this space is built out of not simplices, but quotients of simplices by finite groups, but you can make at least with rational coefficients, you can make a well-behaved cellular homology theory for such spaces. And you can make a relative cellular homology theory for complexes relative to subcomplexes. And then you can try to identify contractible subcomplexes to simplify your calculations. And so here's one such subcomplex. So we call it delta GW. We call it the weight locus. So these are tropical curves that have a vertex of positive weight. So these are dual graphs of stable curves that have a component of positive genus. And the theorem is that this is contractible. So for all G. And so then when we want to compute rational reduced homology of delta G, we can just compute homology relative to this contractible subcomplex. And as I said, there's a cellular chain complex that computes that rational homology. And what we found is that this is a very well-studied complex. So this relative cellular chain complex is canonically isomorphic to Kontsevich's graph complex. So this is studied in his original paper in 1993 on the formal non-commutative symplectic geometry. So the same paper where he made the conjecture on that eventual vanishing for fixed distance below the virtual cohomological dimension. One of the things that's interesting and exciting about this identification is that on the right-hand side, there's an additional structure that is not visible on the left-hand side. So this graph complex, you can now put them together across all genus. So there's an additional Lie structure. So the product over all G of these GG has a natural Lie bracket that makes it into a differential graded Lie algebra. And so then there's a Lie bracket that descends to cohomology, and that Lie bracket is additive in G. So here's a hidden structure on one graded piece of the weight filtration of the cohomology of MG. It forms a Lie algebra. And through the graph complex perspective, this Lie algebra has been extensively studied, and there are pre-existing deep results about the structure of that Lie algebra. And so in case they are not familiar, let me tell you what those deep theorems are about the structure of graph cohomology as a Lie algebra. So here's a theorem of Thomas Wilvacher from 2015. And so if we phrase it in terms of the tropical moduli space, what he says is that the product over all G of H2G compactly supported MG trop. So this is isomorphic to the completed Grothendieck-Teichmuller Lie algebra. The study goes back to Drinfeld. And here, so what's special about this degree 2G? So the compactly supported cohomology of MG trop vanishes in degrees less than 2G. So that's something that one can deduce from our work and the virtual cohomological dimension and the vanishing of H4G minus 5 mg. And Wilvacher had a different proof that uses deformation theory of operads and relations between that deformation theory and graph cohomology. So in any case, on this side, we end up with the Grothendieck-Teichmuller Lie algebra, which is the Lie algebra associated to the fundamental group of a Tannakian category, so the category of mixed Tate motives over the integers. And so that category was studied in earlier work of Francis Brown. So this is celebrated work of Francis Brown, proving 1/2 of a conjecture that is due to, in various forms, to Deligne, Drinfeld, and Ihara. And so the theorem is that this Grothendieck-Teichmuller Lie algebra so contains a free Lie subalgebra generated by classes sigma 3, sigma 5, sigma 7, sigma 9. So there's infinitely many generators, one in each odd degree greater than or equal to 3. And here, this sigma g, we could think of now as being in H2G. So the generator sigma g is in some sense in genus G. I think I still have a bit more time, so let me tell you some properties of these generators. And so so these are cohomology classes. So let me tell you about how they pair with homology. So examples of cycles on delta G. So if we go to the link of the moduli space. So let's go in genus 3, and so there's all the different dual graphs of stable curves of genus 3, and one of those dual graphs is the complete graph K4. And so the automorphism group of K4 is the symmetric group on 4 letters. So this is just the permutation group on the vertices. That's the automorphism group of the graph. And of course, the symmetric group is generated by transpositions. And if we interchange two vertices, then we will interchange two pairs of edges. So if you think of this graph as corresponding to an orthant with one coordinate for each edge, then the automorphism group of the graph is acting by even permutations on the coordinates, and so it's acting by orientation preserving automorphisms on the corresponding cell. And so that means that this cell does have a fundamental class, and so there's this class of K4 in the cellular chain complex of delta G, and then I claim that this chain is a cycle, so the image under the differential is 0. And the reason for that is that the differential, well, that's what happens when you go to the boundary of the cell. So when you go to the boundary of a cell, some edge length is going to 0, and so then combinatorially you're contracting an edge. But if you contract an edge that's contained in a triangle, then you are left with two vertices that are connected by a pair of edges. And then you have an automorphism that just interchanges those two edges. So that's an odd permutation of the edge set, and so that induces an orientation reversing transformation on the corresponding cell. And so then that cell is 0 in the cellular chain complex. And
rationally 0.
Rationally 0, yes. Yes, so the cellular homology theory for these spaces built out of quotients of cells by finite groups only behaves well with rational coefficients. So good, yeah, thank you, Dan. And good, and so then in fact, one can check that sigma 3 W3 is not 0. In fact, sigma 3 paired with W3 is a non-zero rational multiple of zeta of 3. And so I'll come back to that in a moment. And so you can generalize this, and the generalization is not to look at higher complete graphs, but to look at higher wheel graphs. So if you go in even genus, so a 4-wheel, genus 4, this is 0 in the cellular chain complex because it has an automorphism, say reflecting across a diagonal interchanges 3 pairs of edges. That's an odd permutation. So orientation reversing, so it's going to vanish in the cellular chain complex with rational coefficients. But if you go to a 5-wheel, and then there's, of course, a 7-wheel and a 9-wheel. So these are non-zero chains that have, the differential is 0. And so then the theorem is that sigma G paired with WG, and so this is, again, a theorem of Vilvacher, so that this is a non-zero rational multiple of zeta of G. And so this, I hope, starts to bring things a little bit full circle to things that are closer to what Hodge theorists think about, which is that we need to think of this zeta of 3 or this zeta of G as being a period. And so in fact, if we go to Brown's work on the category of mixed Tate motives, so he's studying that category in terms of the periods that exist when there are non-trivial extensions of Tate motives over the integers. And zeta and these many of these periods are multiple zeta values, and so in particular the odd zeta values, zeta of 3 and zeta of G. These are periods that classify certain extensions of Tate motives. And one of the things that's puzzling here is, so I'll say this as a mystery for now. So zeta of G so is a period that classifies a certain extension of Q by Q of minus G. And so one naturally asks, so does this extension live in the cohomology of Mg? And the answer is an immediate no. So even for G equals 3, this extension is not there. So as I mentioned earlier, Lohenge computed the full cohomology of M3 with its mixed Hodge structure. And H6M3 is Q. It has rank 1. There's no extension there. But that's certainly not going to be the end of the story, and it's not it just sort of can't be a coincidence that the proof that these wheel classes are non-trivial involves these special values of zeta, and so there's a theorem of Dick Hayne. So Hayne shows that H6M3 compact type, so a partial compactification living in between M3 and M3 bar. So this is isomorphic to H6A3. And both of these are the extension of Q by Q minus 3 with periods Q star times theta of 3. So the extension is there geometrically. It's not there on Mg, it's there on two closely related spaces. And so one of the directions future work is to extend Haynes' result to odd G at least 5. Okay, and so let me stop there.
All right, thank you very much, Sam. Questions?
I'm waiting for the Hodge theorists to ask the question. I mean, it's your. Well, anyway, so let me try. So you are saying that Hodge theory gives you a piece of the cohomology of Mg, and I guess this is a question that keeps arising. How can you push, I mean, further pieces of the Hodge structure into this calculation? I mean, the image that I have is that Mg is like the Kato-Nakayama space of Mg bar, and the push forward map gives you a lot of the mixed Hodge structure. And well, anyway, so what can you say?
Well, okay, so one way to think about it is you could look at Deline's weight spectral sequence, say associated to the Deligne-Mumford compactification.
Yeah.
And so then you'll have one row that is built out of H0 of all of the strata, with their symmetric group actions, and then you'll have another row that's built out of H1 of all of the strata. Well, all of those H1s vanish right? So we know H1, H3, and H5 all vanish for MGN bars. And so the interesting rows are 0, 2, 4, and then 6, 7, 8, 9. Okay, and so in order to understand, for instance, weight 2 compactly supported cohomology of Mg, then we need to understand the H2, which is the Picard group of MGN bar with its symmetric group action for all smaller G and N. And so this is work in progress, and so I think you will see in the next year or so interesting results about weight 2 below top for Mg.
Thank you. Yeah, great.
Other questions?
I was wondering. So you showed that showed this result that the weight 0 parts of the Hodge structure comes from the tropical moduli space, and just just philosophically, it was not clear to me why you look only at Mg without the compactification, but in the tropical moduli space you have all these stable limits built in. So why does this happen?
Okay. So you can think about this in various different ways. So one way would be to think about boundary complexes, so dual complexes of boundaries of compactifications. And so the link of the tropical moduli space is appropriately interpreted the dual complex of the boundary of the Deligne-Mumford compactification. Another way to think about this would be through Berkovich analytic geometry, that the tropical moduli space is a skeleton of the Berkovich analytification of MG. And then it's a general fact that the compactly supported cohomology of the skeleton of the Berkovich analytification is the weight zero cohomology of the complex analytic space. So that's so I think that's in Berkovich's paper that he calls a non-Archimedean analog of the Tate conjecture. So yeah, so just different ways of thinking about it. But you're absolutely right. So in some sense, your weight zero cohomology knows about the combinatorics of compactifications, and so does the tropical moduli space.
If I may comment on that, so MG feels non-compact, but it's homotopy equivalent to the Kato-Nakayama space of MG bar, or in fact any toroidal compactification. So it's in terms of cohomology, it's the same as something compact that actually lies over MG bar.
That's right.
Can you just repeat a bit about this last part about the zeta free and kind of these extension classes, or do you see those from your perspective, or what was that? Or
yeah. Okay. So right. Okay. So I guess maybe it's familiar to you that these special values of zeta occur as periods when extensions of okay. And so how does it appear in our setting? So so in the work of Wilvacher and his collaborators, one of the things that they show is that there are interesting and highly non-trivial ways of producing graph cocycles. So cohomology classes for graph cohomology, and in fact, like not just the classes, but they produce cocycles from integrals on configuration spaces. So here so for each graph, you then look at a configuration space essentially of embeddings of that graph into the upper half plane. And so the vertices should go to distinct points in the upper half plane. And then you have some interesting maps to S1 so since these are mapping to distinct points, then there's an argument associated to each edge. And now you can pull back the volume forms from S1, wedge them together, and you do this in a clever way, and you integrate, and now you get a number for each graph. And that their construction is set up in such a clever way that if you do this for all graphs, then you get a cocycle. And so then they show that this configuration space integral that they get associated to the wheel graph is zeta of G. And then they relate these configuration space integrals to Drinfeld's associators. And that's how they get the relation to Francis Brown's work. Yeah, so we would love to have a better understanding of how all of these pictures fit together. So how does the Durham cohomology of the Fulton-McPherson configuration space relate to cohomology of MG, relate to graph cohomology? There's a lot of very interesting and intricate pieces.
So this is work in progress, or like a wish list, or?
I would say that is more of a wish list than work in progress. I think we don't see clearly yet how all of these things should relate.
Other questions?
Yes. Hi, Sam. Ages ago, we proved with Maurizio Cornalba that odd cohomology, 1, I guess 1, 3, and 5 of
Yes.
0. So do you have some more results in that direction for MGN, for the compactification, of course?
No. As I was saying to in response to Dan Abramovich's question, so there is work in progress using your work with Cornalba on the Picard group of MGN bar to investigate weight 2 compactly supported cohomology of the open moduli space MGN. But no, we have no further results about the odd cohomology of the compactifications.
Yes, because also there, the basic tool was the delinear spectral sequence.
Yes.
Yes, of course. Good. Thanks.
Yeah.
All right. If there are no other questions, let's thank Sam again for the wonderful talk. And we will resume at 10:30 with a talk by Paul Hacking. Thank you.